Good morning. Thank you for registering for the ongoing Fluid Life Data Interpretation webinar series. Each webinar will focus in on a specific component, covering overall causes of potential issues, and then looking at the oil analysis data to identify key indicators and how to react to them. If you have any questions during or after these sessions, please feel free to send them to customercare@fluidlife.com, and a Fluid Life team member will get back to you promptly. These sessions will also be recorded on fluidlife.com for you to listen to after this session. I'm Mo Habib, account manager for oil and gas, and I'll be your host today. This session will focus on natural gas engines. Let's talk about the data interpretation process. If we really think about it, it can be broken up into three parts. The first is interpretation of the results, which is reviewing what has been flagged, reviewing the hours on the oil or component, and looking into recent repairs or issues which could have driven these flags, and getting additional perspective from the lab, OEM, oil supplier, and other sources to determine how to react. Next, you take this information and decide how or if you're going to react. You make the call. This leads to your response, ranging all the way from not doing anything, to gathering some more perspective, to monitoring closely, all the way down to changing your PM intervals and even creating improvement projects. So let's begin with an overview of natural gas engines. Natural gas engines are very unique. They operate in locations ranging from extremely cold to extremely hot. This also makes them quite versatile. I don't want to get too much into choosing the appropriate lubricant, but here are a few things to think about. Because natural gas burns hotter than diesel fuel or gasoline, lubricants for natural gas engines can operate under severe heat stress. Because the natural gas burns hotter than diesel fuel or gasoline, the lubricating oil for natural gas engines can operate under conditions of severe heat stress where temperatures exceed 90 degrees Celsius. Particularly in certain areas within the engine, such as the cylinder walls, piston undercrowns, and valve guides. This is a little to the engine's long-term health. Natural gas is a dry fuel. It needs to be used with lubricating oil that produces oil ash as a byproduct of combustion. In the right concentration, ash will form a deposit on the seating surface of the exhaust valves that are needed to prevent what is known as valve recession. When the proper amount of ash is present, not too much or not too little, the faces of the exhaust valves and their hard metal seats located in the cylinder head are protected against recession. Too much ash, on the other hand, can permit excessive deposits to form and cause hot combustion gases to leak around the valve seats, which leads to burning them. Overly thick ash deposits can also behave as unwanted insulators. It kind of impedes the natural flow of heat away from the valves. The classification system used automobile oils doesn't apply to natural gas burning engines. Let's take a quick look at an OEM spec sheet before we get into the data. These are the testing limits for Waukesha engines. These are, of course, available for most manufacturers and is a great guide to where to set your flagging limits. Fluid Life takes these specs into consideration, as well as compares your sample results to those of others in the same industry, using the same equipment, using the same oil, and all that information, these distribution analysis plots. This gives you an idea of where you are relative to where everyone else is, using the same oil, using the same equipment, in the same industry. One of the most effective and least expensive natural gas engine condition monitoring techniques is, of course, oil analysis. The oil analysis tests that should be considered standard, and the ones we're going to focus on today are viscosity, nitration and oxidation, glycol contamination, spectrochemical analysis by CP, base number, acid number, and isoparticle count. So let's get started and take a look at some analysis reports. Let's start with the first thing you should look at when reviewing your oil sample, namely the viscosity. The viscosity is a key indicator in your oil analysis. This test should ideally be performed at both 40 and 100 degrees Celsius. An increase in the viscosity can indicate conditions such as oil thickening, which can be an indicator of oxidation nitration. Increased contamination levels or increase in insolubles. A reduction in viscosity can be indicative of dilution in the oil or even shearing of the viscosity index improvers in multigrade oils. In this sample, we see the viscosity has gone up to a reportable level, then back up to reportable again, as you can see here. There was indication of an oil change at the first flag, which may have led to the viscosity readings going back to acceptable levels. The first thing you want to do if the viscosity readings are high and there are no other flags is to confirm the oil is labeled correctly. A mislabeled oil can provide incorrect data, causing false flags. The next thing you should do is take a resample. This would confirm if there was, in fact, an issue not contributed to things like improper sampling techniques or sample contamination. This particular sample, however, is only half the story. Here is the full sample results. As you can see, the spike in viscosity is due to nitration and oxidation. Nitration and oxidation occur naturally within natural gas engines and can be quite severe. Oxidation is caused by the reaction of oil with oxygen in combination with catalysts such as copper wear particles. This occurs to some degree in all lubricated systems and leads to an increase in the oil viscosity as seen here in this report. Nitration is a chemical reaction within the oil, which can cause serious and premature thickening of the oil, resulting in severe varnish and carbon deposits. It occurs mostly in natural gas engines and can cause serious issues like complete solidification of the oil if not controlled. It's also shown that once nitration begins, it can worsen exponentially. In this sample, the oxidation and nitration levels indicate overheating, localized hotspots, and this may be due to overextended drain intervals. One way to get on top of this, of course, is to shorten the drain intervals. Let's move on to our next report. Spectrochemical analysis through ICP measures the level of wear metals and the concentration of the additive elements. These are reported in parts per million and provide an indication of the rates of wear of engine components and the depletion of additives. There are three things to wear particles analyzed are generally limited to 5 to 6 micron range, which would indicate that the results are the results of wear, but not the cause of it. In order to get reliable data using SPEC, you should run at least 3 samples to establish a wear trend. Each engine will exhibit its own wear fingerprint, which means that the data collected is essential in verifying if there's any possible issues. Once again, make sure to get at least 3 data points. At Fluid Life, we test for 23 elements using the ICP. And let's take a look at some examples of common wear metal issues. In this report, you can see that iron, copper, lead, and chromium are high. Let's take a look at these individually and as a collective. Iron wear is generated from most engine parts, including the crankshaft, cylinder liners. Iron wear can also generate from the camshafts, rods, wrist pins, timing gears, rings, shafts, and valves. Lead found in the engine oil may originate from the journal bearing overlay material, such as Babbitt. In some cases, it may be found as an oil additive or a contaminant from solars. A copper could originate as a wear metal from cam bushings, thrust washers, and or cooler coils. We recommend changing the lubricant at any applicable filters, if not recently done. If necessary, you should flush the component before refilling. Chromium wear can be generated from the rings, liners, exhaust valves, and shaft plating. And chromium can also be generated from stainless steels like shafts, valve trains, and rollers. In this sample, you can see a steady high and severe flag for all these metals: iron, copper, lead, and chromium. The first thing you want to do is take a resample to confirm that these are in fact the issues. In this case, you see a steady trend of the wear metals going up, which means that you should change immediately, or change the oil immediately and take a look at this right away. The next thing we want to look at is the base number. The base number is an indication of the reverse alkalinity contained in the engine oil. Basically, it's an indicator of the level of detergent and dispersant additive package's ability to counteract the acids. Standard testing is ASTM D2896, providing an accurate indicator of the base number. These results can be compared to the unused oil's base number. Once again, this is why it's very, very important to make sure that you have a reference oil in your sample. That way we were able to compare the base number to the reference oil base number. Because most natural gas engine oils are formulated as low to medium ash oils, the base number will generally be in a range of 3 to 7. These levels may not be sufficient to protect engine using dual fuels. Base number is also an important oil analysis test when the fuel in use contains high levels of sulfur and organic halogens, such as chlorine and fluorine. When high sulfur sour gas or landfill gas is in use, the typical natural gas oils available may not sufficiently protect the engine from the acid components. In these cases, the engine operator may need to shorten oil drains or select an oil with higher base number, which will provide higher level of alkalinity. A general rule of thumb is that base number reaches the end of its useful life when reduced to half of the new oil spec. The next thing we want to chat about is the acid number. So the acid number is an indication of the increased acid levels in natural gas engine oils. Acid number testing is often a good way to find your optimum oil drain intervals as well, particularly those in natural gas engines. A high acid number is an indicator of nitration, oxidation, and contamination. As opposed to the rule of thumb for base number, the general rule of thumb for acid number is that when an acid number doubles that of the new oil value, the oil is nearing its condemning limit. As seen in this sample, the acid number is increasing along with nitration right here. So as discussed earlier, nitration can lead to the reduction in the component life, and in this particular case, the oil or filter should be changed. Just a quick note with acid and base numbers. In case you're not aware, they are not correlated. So the base and acid numbers don't increase and decrease together. So it's good to run both. The next thing we want to chat about is the ISO particle count. Although you can get information from the wear metals themselves, relying on spectrochemical analysis alone can only catch particles between 5 to 6 microns, as mentioned. This is one of the reasons where isoparticle counts would come into play. Isoparticle count testing can track bigger particles. As you can see, there's a lot going on in this sample here. If you take a look at the history, the oil has gotten to a point where the isoparticle count was unable to be performed right here. You can see high oxidation and nitration occurred as well. As the oil change is done right after this, it did help down. However, after a few samples, it went right back up. As mentioned earlier, once the nitration starts in the natural gas engine, it can worsen exponentially, and this can be seen here. So even with nitration and oxidation still occurring. The recommendation in this particular sample is to either change the filter, the oil, and take a resample immediately. This is also a sample where you'd want to review your oil drain intervals and possibly consider shortening them. In this sample, the particle count is trending up, and then the oil change particle count goes down. And then over time, it trends back up. This can be evidenced through the iron, copper, lead, and chromium going up, dropping off, and then going down again. So the big issue, and this ties back into nitration with the oil thickening, is something called boundary lubrication. This is what happens when the oil becomes too thick, and therefore it doesn't move efficiently. And this causes metal-to-metal wear, which can be very severe for your components. The last report we're going to look at shows a coolant leak. This sample contains extremely high sodium and potassium. This is indicative of a glycol contamination. As you most likely know, testing for glycol leaks is a must for any oil analysis program. Any amount of glycol in the analysis can indicate a coolant leak into the engines and may cause catastrophic failure by promoting corrosive acids, sludge, and varnish to form quite rapidly, as well as causing a reduction in the oil film, which can suddenly increase wear. This report's an extreme example. Coolant contamination can result from defective pump seals, improper torqued cylinder heads, crack heads, or block. In any case, the first thing you should do is resample to confirm that there's actually a coolant leak. If the report continues to indicate coolants, the next step is to shorten the odor intervals and oil sample intervals to at least 1/2 until the glycol is normal. And while this is happening, you should try and find where the leak is. An interesting thing in this particular sample here is you see that there's very minimal glycol in these points here, and then all of a sudden a spike. This indication could be an indication that there could be some burnt glycol. So this brings us to the end of today's webinar. Thank you for participating in these. Our next one will be on July 15th at 9 a.m. Mountain Standard Time, and it'll be focused on diesel engines. Once again, for any information and for any questions or inquiries, please email customercare@fluidlife.com and we will get back to you promptly. Thank you again for attending today's session. Thank you and have a great day.